Let's do an example now that's similar to one we did earlier, but we'll layer in a little bit of that transverse velocity. So we have a sinusoidal wave traveling in the positive x direction to the right. It has an amplitude of 15 centimeters, wavelength of 40 centimeters, or 0.40 meters. Once you have wavelength, you have an idea that you can go ahead and find k, your wave number. The frequency is 8 hertz. That means you can find the angular frequency and the period. And once you know f and lambda, you can also find the wave speed. The vertical position, so it's talking about the height of an element of the medium, so a little piece of string at t equals 0. So this is a picture of our wave at t equals 0 and at x equals 0. So that's this spot right here. That height is 7.5 centimeters. We write that down by saying y of 0, 0 equals 7.50 centimeters. If you're more of a symbols person, you might write that down as a over 2 because it's half the amplitude. Okay, part A. Find the angular wave number k. K we know is 2 pi over lambda. 2 pi divided by 0.40 meters gives us a wave number of 15.7 radians per meter, or meters to the minus 1. Okay, what is the period t? Period t is 1 over frequency, 1 over 8 hertz, equals 0.125 seconds. Period's done. Angular frequency omega is 2 pi times the frequency, 2 pi times 8 hertz. That gives us an angular frequency of 50.3 radians per second. Omega is done, and the speed of the wave. Two ways to find v. You can do omega over k, or you can do lambda times f. They're both the same, doesn't matter which one you choose. I'll do lambda times f. 0.4 meters times 8 hertz equals 3.2 meters per second. Okay, part B is a little trickier. We've got to find the phase constant. Phase constant is a little bit trickier to find, and we have to use our initial conditions. So we have to use the fact that we know that y is 0.57 when x and t are 0. We're doing that because we know the phase constant is in the equation for y. Let's get started and see where we get. So the general expression for the height of that wave as a function of position and time is y of xt is the amplitude times cosine kx minus omega t plus phi. Careful here to remember that we're using minus because the wave is traveling to the right. If it were leftward traveling, we'd have a plus. Now let's put in the point that we know, which is that if y at x equals 0 and t equals 0 is going to be a times cosine of k times 0 minus omega times 0 plus phi. Let's simplify now. Our y value is 7.50 centimeters. Amplitude is 15 centimeters. Oh, I wanted my 5 squished a bit there. 15 centimeters times cosine k times 0, 0, omega times 0, 0. So we're left with cosine phi. Divide both sides by 15 centimeters. Now we'll take the inverse cosine of both sides to get that phi. When you do this on your calculator, remember your calculator is in radians mode. So that's the inverse cosine of 0.5. Your calculator is going to tell you 1.05 radians. And that's a true answer. If you do cosine of 1.05, the result you're going to get is 0.5. But is that the only answer? And no, that is not the only answer. 1.05 radians is not the only angle for which, when you hit the cosine button, your answer is 0.5. It's the angle in the first quadrant, and your calculator always wants to give you an answer in the first or second quadrant. But you also have an answer down in the fourth quadrant. Both of those angles have the same value for cosine. So I'm drawing the unit circle here. You probably did a little bit of that in your high school geometry or trigonometry. So cosine of 1.05 is 0.5, but cosine of 2 pi minus 1.05 is also 0.5. Or cosine of 5.24. And by all means, please do check it out. Grab your calculator, do cosine of 1.05, do cosine of 5.24. You'll see that you get the same answer. So where cosine is a multivariate function, it has answers in different quadrants. There's more than one answer. When you're doing these problems, you always have to think, what are my two answers? Okay, I have two answers. What am I supposed to do about that? They can't both be right. How am I going to figure out which one is right? I need another condition. That's going to come from my initial velocity. So now I have two answers for my phase constant. If I want to narrow it down to the correct answer, I need another initial condition, and that's going to come from my initial velocity. So my transverse velocity, you get that expression by doing the derivative of the position as a function of time. That's going to be a times omega times sine of kx minus omega t plus phi. My initial velocity at x is 0 and t is 0, it's going to be a times omega times the sine of 0 minus 0 plus phi. Okay, so this tells me if I know if my velocity is positive, then my phi has to be positive. If my velocity is negative, then my phi has to be down in the fourth quadrant. So I need to figure out that initial velocity. How am I going to do that? Well, let's think about this wave. This is a sinusoidal wave and it's traveling to the right. So the direction of my wave is to the right. This is a picture of my wave at t equals 0. That's the black line. A little bit of time later, this wave will have moved to the right. And what that's going to look like is, I don't draw super well, but hopefully you kind of get the idea. The red dashed line is my wave having moved to the right. So that's a little bit of time bigger than 0. Now let's focus in on that little bit where x is 0 and t is 0. So that initial spot right there. So this little bit of string, that moved downwards. So as my wave moved to the right, the little bit of string at x equals 0 and t equals 0 moved down. That tells me that my initial transverse velocity is down or negative. Okay, now I've got another little bit of information. So if my phi is equal to 1.05 radians, then my initial velocity, Vy of 0 and 0, is a times omega times sine of 1.05. That turns out to be positive. If my phi is 5.24 radians, then my initial velocity is a times omega times sine of 5.24. That turns out to be negative. The positive is wrong because that would mean the string is going up. The negative is correct because the string is going down. Now I know what my phase constant is. My phase constant must be 5.24 radians. Now to finish part B, write a general expression for the wave function. So that means write that y of x and t, start with the general expression, a times cosine kx minus omega t plus phi, and then fill in your numbers. Y of x and t is 15 centimeters times cosine of k, that was 15.7 radians per meter. That's times x minus omega, omega was 50.3 radians per second. That's times t plus the phase constant, which is 5.24. You can write in radians if you wish, but you don't need to. This example is more or less a repeat of the previous example, so I'm not going to include this as part of the lectures. I'm going to leave it for a homework example. Just in case you do find this tricky though, I think I will make a video and I will post it with the lecture notes, but it's not officially a part of the lecture, just a little bit of extra if you want some extra practice.